Hello, everyone. My name is Felipe Matheus Franco. I am a first-year PhD student with Professor Alexander Chikansky, and this is my poster presentation for MECH 6000, Impact Analysis on Non-Planar 3D Printed FFF Parts. So for the introduction, we have 3D printing, and 3D printing is a process that is sequential in order to deposit material in sequential layers to achieve our final part. These layers can be in any format, but usually we make planar layers equidistant from the printing bed, which is also usually planar, flat. And this is a very straightforward way to introduce the slicing process in our part in order to achieve individual layers which we can print one over the other to achieve our final printed part. This is very easy, very straightforward, very easy to apply, but carries with it an inherent anisotropy, which is the difference in properties when you get that printed part and stretch it in different directions. So, for example, usually when you have the parts printed in a planar way, the build direction, which is the z direction, is weaker than the normal x and y directions because the material delaminates and the layers detach instead of only withstanding the stresses with the material properties. So this is a problem because that makes the parts very anisotropic, and that hinders the application of 3D printed parts in many activities in the engineering uh, world. So we introduce the tests here with non-planar 3D printed parts. Uh, the idea is to get these parts here, planar and non-planar. So here we have a vertical specimen with sinusoidal layers, and we also had one with the planar layers. A horizontal specimen with the sinusoidal layers and one with the planar layers, and one bell-shaped, which is mostly planar, but on the center of the specimen, it gets this bell shape around the notch. Uh, we got these parts with the amplitude frequency that our machine could handle because it's a 3 degree of freedom machine. So it is very limited in the angles it can print. And we submit these parts to impact test, Sharpie impact test, which is ASTM 6110, D6110, which is a standardized way to measure impact strength. In order to fabricate the parts, I had to devise these buffer layers, which are these intermediate layers between the slicing I wanted and the flat part on the bottom, which is the build plate, and on the top, because the specimen for the Sharpie impact test is a rectangle, it's a prism, so it needs to be flat on the top as well. So I had to recompensate those layers. And we did the impact testing with the 10.8 joule hammer. The results, you can see here that mostly the sinusoidal vertical sample presented a 50% increase over the planar vertical sample. This is because of the fact that the planar sample here, this is the fracture surface. The impact comes from above. Here's the notch. And you can see that the crack in the sample is also sinusoidal because, as I told you, the sample tends to detach the layers instead of breaking. because the interlayer bonding is a little weaker than the material itself. So the planar one, uh, purely delaminated, so you can see it's a very clean fracture, and it's just one of these layers which is detached from the other part. So it's a very smooth fracture, and that doesn't take a lot of energy to fracture. And the sinusoidal vertical sample has more path and has a more rough uh, fracture surface, which means that the crack had to use more energy of the hammer to break. And here you can see the comparison between them. As for the horizontal ones, they all had pretty much the same result. The error bars here indicate that I cannot say that they are statistically different. And that is because for the impact test, uh, for the for the direction of the test, the horizontal orientation is already the optimum orientation. So either planar or sinusoidal or bell-shaped, they were mostly horizontal, so the differences are not representative. And we can see that they all have a very similar fracture surface between all of them. Even then, if uh, I would say that the bell and the sinusoidal horizontal sample, they have a little advantage. That would be because when you print the samples here, you can see that you have an accumulation of material just under the sine wave here, and that also happens for the bell sample, that accumulates material in this part and makes it a little tougher. So maybe we need further testing to see if we have some different and significantly different results. But as it stands, I cannot confirm statistically that the bell-shaped or the sinusoidal-shaped are stronger in the horizontal direction, only on the vertical direction. But something that we can say here is that between the planar vertical and planar horizontal, which is classical anisotropy, the difference in anisotropy was 250%. So average 4.7 here for horizontal and average 1.36, 1.37 for vertical. And for the same slicings and only changing the orientation, for the sinusoidal ones, which are also a pair, the average was 2.06 for the vertical and 4.81 to the horizontal. So the anisotropy between these ones, sinusoidal, was lower than the anisotropy between the planar ones by roughly 50% as well. So it's a very interesting result that we can take home in order to make more isotropic parts using the same machine, the same material, the same output geometry, but having a little bit more isotropy on our parts, which is good if we have a part which we don't know how it's going to be loaded when it's in use. The load is not known, because if it is known, we can optimize for it. If it's not known, it's good to have isotropy. Some final remarks. You can see that as the layer for the non-planar specimens is printed, we have a little delay of movement and of um, material deposition, which was described in literature by one of the developers of the slicers that can produce these non-planar parts, because we have a little inertia in the direction of movement. So when it's going right to left, it has inertia to one side, and when it's coming back left to right, it has inertia to the other side. So they crisscross, and that further helps the internal part of the sample to be a little more fuzzy, not so smooth as the planar sample that we can see here. So you can see it's more fuzzy, and that helps the sample to withstand more energy before breaking. So we need more energy to break the sample, and that's the purpose of the impact test. So for quick conclusions here, we can see that the vertical specimens had a significant enhancement against impact for the Sharpie test. The horizontal specimen didn't show much improvement because there is no much room for improvement. It's already a very good orientation for the impact test. We can safely say that for the one that had room for improvement, we reduced the anisotropy, which is usually a very good thing to reduce in our printed parts. And for future works, um, by incorporating multi-degree of freedom capacities in our printers, we could help to reduce this kind of error and understand if this increase in properties is due to the machine not being able to replicate my slicing correctly and thus making a rougher surface, which uh, by chance helps in the mechanical properties. Uh, and if we have also more degrees of freedom, we can try to think of different toolpaths that would maybe be stronger than only sinusoidal. So we can have different sinusoidal properties or even another shape that we can produce with a printer with a higher degree of freedom, but we cannot with the current printers we have. That's it. Thank you very much. And I appreciate your attention.